Welcome back. Now our next tech talk will be looking at learning with weak supervision. Our speaker is a professor in the School of Computer Science at Carleton University, a Canada Research Chair in Machine Learning, and a Canada CIFA AI Chair at AMI. Her research interests span machine learning, computer vision, and natural language processing, with an emphasis on expanding the autonomy of machine learning methods by reducing the dependence on extensive human guidance and extending applicability to a more diverse annotation scenarios. Please give a very warm welcome to Dr. Yuhong Guo.
Hello, everyone. So my talk today is about learning with weak supervision. So the advances in machine learning have led to many successful applications in the industry. Supervised learning actually is a foundation for many of such recent successes. The problem of supervised learning can be stated as follows. Given a set of annotated training data, we learn a prediction function. This prediction function can map any instance in the input feature space X to a vector in the label space Y. For example, for document categorization, our input will be documents, and the output labels will be the document categories. For object recognition, the input will be the images, and the output labels will be the object categories. After we learn such a prediction function, and then we can apply it to predict labels for the new instances. However, supervised learning has a fundamental bottleneck. That is, standard supervised learning algorithms need to train prediction functions with strong supervision knowledge. They require a sufficient amount for accurately annotated data. In reality, it is difficult and expensive to accurately annotate a large amount of data. If we use experts for annotation, so this process is going to be expensive, time-consuming, or even impractical in some domains. Facing such difficulties, one strategy is to exploit other sources of annotations. For example, if we exploit auxiliary annotated domains, and this leads to domain transfer learning and domain adaptation. If we exploit low-quality annotations, then this will lead to weakly supervised learning. Weakly supervised learning is about leveraging higher level or noisy input from the annotators. The figure here actually shows many different research directions for answering the question how to get more labeled training data. And weakly supervised learning is one primary direction. In today's talk, I will focus on a special type of learning scenarios with weak supervision, that is partial multi-label learning. The problem of partial multi-label learning is we learn a multi-label prediction function from a training set S, where each instance xi is annotated with an overcomplete candidate label vector yi. Here, the overcomplete assumption means the candidate label site indicated by the label vector yi contains not only all the true labels, but also some additional noisy labels. Partial multi-label learning scenarios can arise in many different domains. For example, when we use summary annotations for group samples. As shown in this figure here, for person recognition problem, we can collect a set of names from the movie script as a candidate label site for a group of images for the corresponding movie scenes. So in this case, the candidate label site will be overcomplete for each individual image. A more general scenario comes from crowdsourcing. when we use crowdsourcing for data annotation, the annotation quality is unguaranteed. To prevent missing labels, we can use multiple annotators, right? For example, for object recognition, we give this image to multiple annotators. Then we collect all the object labels returned by multiple annotators together as a candidate label set for this image. And then this candidate label set contains not only all the true labels, but also some additional noisy labels. Hence, it will be overcomplete, and we have a partial multi-label learning problem. The challenge of partial multi-label learning lies in, for each instance, the true labels, Zi, are hidden within the candidate label set in Yi. And also, we do not know the number of true labels. Facing this difficulty, the key issues we need to address are how to identify the true labels. That is, how can we perform label disambiguation, and how to learn the predictors. Next, I will present an adversarial partial multi-label learning model termed as partial multi-label learning GAN to address the partial multi-label learning problem. The idea is to unify label disambiguation and prediction model induction under a generalized encoder-decoder framework and build bidirectional inverse mappings between the feature space X and the disambiguated label space Z. The process can be stated as follows. Given the training data, where we have the input instance in the input feature space X, and we also have the candidate labels Y. But we do not know the true labels Z. So what we're going to do is we introduce a label disambiguator d delta to recover the true labels. And then we learn an inverse forward mapping using a label predictor to map the input features into the labels Z. Meanwhile, we also learn a data generator G, which forms the inverse mapping, maps the true labels Z into a vector in the feature space X. So the label predictor F and the data generator G form the encoder and decoder of the proposed model, respectively. Now let's look at each part in detail. For label disambiguation, we introduce the label disambiguator d delta to predict irrelevant labels from the input features X. And then we can obtain the true label vector Z by dropping the irrelevant labels from the candidate label vector Y, as shown in this equation here. The ReLU function we have here is trying to limiting the irrelevant labels within the candidate label site in Yi. For the encoding process, we learn the label predictor F by minimizing a classification loss on the training data with the disambiguated labels. So here, in this equation, the LC denotes a standard classification loss. The targeted labels here, ZI, is the disambiguated true labels. For the decoding process, we learn a data generator G. First, we use the data generator G to generate the training data from the disambiguated true labels through a generation loss. So look at here. So in this generation loss, we try to minimize the difference between each training instance xi and the generated instance from the disambiguated label vector zi. Moreover, to prevent the potential overfitting problem to the specific training instances, we further deploy a GAN model to enhance the learning of the G through an adversarial loss. So for the GAN model, we introduce a discriminator D. And with this adversarial loss, the generator G and the discriminator D play a minimax adversarial game to generate data that is hard to distinguish from the real training data. So finally, we can put all those three parts together to form a partial multi-label learning GAN model as shown in this figure. So this model has three loss terms: the classification loss, the generation loss, and the adversarial loss, right? And then we can integrate those three loss terms together to form an overall learning problem. So our overall learning problem will be a joint min-max optimization problem as shown here. And we have the three loss terms. And we can solve this joint min-max problem by using a stochastic batch-wise gradient descent algorithm. Moreover, if we look at those three loss terms in this model, actually, we have the following dependence relationships as shown in this undirected graph. So that is, given the label disambiguator d theta, the predictor f is conditional independent of the GAN part. So because of this, we know, like by learning these bidirectional inverse mappings between X and Z, we expect to not only enhance the input label correspondence, but also enforce accurate label disambiguation, with the ultimate goal of inducing a good multi-label predictor F. Okay, so this is a proposed model, and then how does it work? We conducted some experiments using multiple partial multi-label learning data from multiple types of data set, including text data, image data, music data, and biology data. First, we compared this partial multi-label learning GAN model with a supervised learning baseline. So the results show here the average precision results on 12 partial multi-label learning data sets. So the blue color shows the results of partial multi-label learning, and the red color shows the results for supervised learning baseline. So we can see, obviously, by performing partial multi-label learning, we can achieve substantial performance gains. We also compared the proposed model with a number of state-of-the-art partial multi-label learning methods. So in each experiment, we use a pairwise t-test to evaluate whether the partial multi-label learning GAN model can significantly outperform each of the other methods. And we conducted in total 196 experiments using multiple data sets and multiple evaluation metrics. And we counted the number of significant wins, significant ties, and a significant number of losses for the proposed partial multi-label learning GAN model. And the figure here shows those recorded counts. And we can see the number of significant wins of the partial multi-label learning GAN model shown in the blue color dominates in each case. And this result clearly shows this partial multi-label learning GAN can significantly outperform the other methods. Finally, I want to conclude this talk by stating that it is important to reduce the dependence of machine learning algorithms on precisely annotated data and increase their applicability. And learning with weak supervision is a general problem that arises in many domains. The encoder-decoder framework is a general and effective approach for learning from weak and noisy annotations.
Thank you very much, Yuhong, for that extremely informative talk. Very interesting indeed.